Okay, hello everybody. My name is Professor John Binner of the University of Birmingham in the United Kingdom. And this presentation is going to be on the processing and characterization of ceramic matrix composites and ultra-high temperature ceramic matrix composites. And it should last somewhere around 45 to 50 minutes. So I'll start off by giving you a little background to myself. I got my bachelor's and PhD in ceramic science and engineering at the University of Leeds in the United Kingdom. That was a few years ago now. And since then, I have been a faculty member at UCLA in the United States and also at the universities of Leeds, Nottingham, Brunel, Loughborough, and now currently Birmingham since 1984. So in another 2 or 3 years, it'll be 40 years since I first became an academic. You can see there that I have published a number of papers and contributed to books and patents and research grants, and I've supervised around about 85 PhDs and postdocs in my career so far, with 9 PhDs and 5 postdocs in my current team. And you can see I've worked on a very wide range of different processing approaches and also a very wide range of different ceramic materials. So that's just one page introducing me to you. So the talk itself is primarily interested or focused on, whoops, I'm sorry, it's gone backwards. Come on, behave yourself. There you go. There we go, that's my next slide. So the talk itself is on high and ultra high temperature materials. And there are many applications that require these materials. They require a combination of low mass, excellent mechanical properties at really sometimes quite high temperatures, resistance to mechanical and thermal shocks or cycles, and of course also chemical resistance. And you can see some images here of just a few applications where these materials are required. And in fact, apart from the bottom right-hand corner, very high temperature nuclear reactor, apart from that one, I have worked on every single one of these applications. And what this talk is going to be is about some of the work that we have done in making these materials. So, we know it's 2021, we know that some materials already exist. So the questions that need answers are, is it going to be possible to take existing materials and then improve them so that we get the right strength and toughness and resistance to oxidation and so forth at these high and ultra high temperatures? Or do we need to develop completely new materials? So that's the first question. When we've answered that question, we need to ask ourselves the second question. Can we make components, and if we can, is their behavior representative of the inherent material properties? It's one thing to make a piece of ceramic or material in the laboratory that measures 1 or 2 centimeters in size. It can be quite different to make a full component. And can we get the properties that we can get in the small lab size samples? Can we achieve those same properties in the components? And then the third question, and this is a question we need to consider all the way through the research. Can we make parts at a reasonable cost? There is no advantage in having the most fantastic material ever developed by human beings if nobody can afford to use it for anything. So we really need to make sure, as we're developing the answers to the first 2 questions, that we keep an eye and we bear in mind, is this going to be something that can be done at reasonable cost? Will people actually use the materials at the end of the day? Okay, so the actual talk itself is divided into 4 parts, not of equal length. So in the first part, I will look at oxide CMCs, ceramic matrix composites. And these are materials which are typically used to around 1000 to 1200 degrees centigrade. So these are the lowest temperature materials that we're looking at. Then I will move on to look at the silicon carbide based ceramic matrix composites. And these are capable of operating somewhere in the range of 1300 to 1500 degrees centigrade. And then we'll finish off by having a look at the ultra high temperature ceramic matrix composites, and these are intended for use at 2500 up to 3000 and possibly even beyond 3000 degrees centigrade. And you will see that there are some similarities and there are some differences in terms of how we go about doing things and what we do. And then at the end, I will provide a summary, and then we can have a session, hopefully, with some questions from you. So let's begin with the oxide composites. So these are known as ox-ox composites. They are oxide fiber with an oxide matrix. And we have a number of projects currently in my team which are focused on these materials. Our focus is on how to make them, the processing of the CMCs. And you'll see that that is pretty much our focus with all of the work we are doing. We are a team who very much focus on how to make the materials. On the illustration there you have got, the schematic is of the next generation of civilian jet engine. The idea is that we'll have a gearbox which is represented by AGB, and that gearbox will need protecting from the heat coming through the jet engine itself. So what we are developing is the heat shield. It's a simple piece of insulating material, but it has to take some quite interesting conditions, as I'm sure you can imagine. So the goals are focused on controlling the mechanical, the thermal, and other properties. And we're also looking very much to develop multifunctional properties. And we're looking at these with a number of different partners, different projects with different partners. And in the UK, these partners are Rolls-Royce, BAE Systems, and DSTL. DSTL is the Defence Science and Technology Limited, and it's part of the military. Now, before we go any further, I really want to make one thing clear to you, and that is there are different types of ceramic matrix coating. And these different types come about from the different mechanisms we use to achieve the toughening effect that we get in these continuous fiber ceramic matrix composites. So one thing we can do is we can put a fiber coating on the fibers. And what that does is it creates a weak interface between the fibers and the matrix. And these are known as weak interface CMCs. And it's one way of making CMCs. It's actually the preferred way of making CMCs. You get the CMCs that are strong and tough, and that's exactly what we want. However, it's not possible to do that with every CMC system. So an alternative approach is you create a very porous matrix, and that gives you a weak matrix. Again, you get the toughening effect, but now the composite is much weaker. So you have a tough but weak composite. So that is less desirable than the weak interface where you have a tough and strong composite. But those are the two primary approaches. So you will hear me talking about weak interface composites and weak matrix composites. The third approach is rarely used. It's a sort of combination of the two. So you go for a weak interface, but you achieve it by having porosity. And so you put in a coating and it's what's called fugitive. In other words, it will burn off, and it will therefore leave a narrow space between the fiber and the matrix. That's a third approach. It works. It gives you a sort of intermediate performance, but to be honest, it's not often used. So the weak interface and the weak matrix are the two main approaches, and these are the two approaches that will be discussed throughout the rest of this presentation. And for the oxide we are talking about, these are weak matrix composites. So we're going to focus for the next few slides on weak matrix, and these are the oxide that we're talking about. So the goal here is to make ceramic matrix composites based on alumina or another oxide, but mainly on alumina fibers with a porous alumina or another oxide, but mainly alumina matrix. So they are oxide fiber, oxide matrix composites, and most of our work and most of the work in the world is based on alumina. What we are looking at is several different processing routes. There's more than one way to achieve that, and so we are looking at different routes and then working out their advantages and their disadvantages, and so we can work out for each different application, because we have more than one, which is the best route to use. And the key requirements are how easy it is to form the shape, how homogeneous is the product, what is the final density. Remember, these are weak matrix composites, so we want a low final density. And then the final properties, how tough are they, how strong are they, and so forth. And as I have said, a major focus of current work is developing multifunctional properties. And you've got a small number of illustrations there. Bottom left-hand corner, you've got a nice purple glove. The main thing about that is a fabric layer, and you can see how easily bent and deformed it is. These are not stiff materials until after they are fired. Then you've got a thermograph. What that does is you apply a heat suddenly to the surface of the material, and then you look at the residual temperature, and it tells you a lot about the thickness of the layer and any flaws or problems you have got in the system. There you've got, in the middle picture, you have got a photograph of the sort of composites that we are making. You've got a microstructure showing you the microstructure of the materials, and then on the right-hand side, these are test bars that we have broken. And the crucial thing here is they have not snapped in half. They have bent. The fibers are still connected in many ways, and so failure is not catastrophic. Failure is gradual, and that's exactly what you want in these ceramic matrix composites. Now, recently, and this means the end of last year, we started a major new program. It's funded by the European Commission as part of its Horizon 2020 program. It's led by the University of Pisa in Italy. It involves 13 academic and industrial partners from a number of countries, as you can see there. The University of Birmingham is involved in this. And the key goal is to learn how to reduce the costs for making ceramic matrix composite components and their use in energy-intensive sectors such as steel making. So we're using these to try and improve the energy performance of other industries. The majority of the work going on is on silicon carbide composites, but our role at the University of Birmingham is slightly different. We are investigating oxide CMCs, just as I have mentioned, and in particular, what we're looking at is the potential to actually make weak interface oxide composites. Now, I said earlier, the oxides are generally weak matrix, and there is a reason for that. Back 30 years ago, nearly 25, 30 years ago, in the 1990s, oxide composites started to be developed. People were unable to make weak interface oxide, so they developed the weak matrix. What we are saying is that, okay, that's fine, but that was 25 years ago. maybe, just maybe, there are some ideas out there now which didn't exist in the 1990s and that allow us to think that we might be able to achieve what has been regarded as impossible, which is to create good weak interface Oxide composites. So that's our target. And the way we are doing it is to use a process known as chemical vapor infiltration. I will say more about that later in this talk, and in particular using microwaves to heat the materials during chemical vapor infiltration. We're going to be having a look at two things in particular: the weak interface, that's our primary goal, but we'll also be looking at that fugitive approach, the third approach that I mentioned that not many people do. We will spend a little bit of time, not much, but a little bit of time looking at that. And then what we will do is we will compare our result with the more standard weak matrix Oxide CMCs made by conventional processes. So this, by the end of the program, which is 4 years long, by the end of the program, we should have a very good idea that either, no, you still cannot make weak interface CMCs, or yes, you can. Here are the properties, and this is one way of making them. Okay, so that's all I wanted to say really about Oxide composites. Obviously, I've got 3 different types of composites to get through, so that finishes off the work on Oxide. And now we are turning our attention to the higher temperature materials, and that is the Sig composites, as they are known, silicon carbide based composites, and also the ultra high temperature CMCs known as UHT CMCs. And with both of these types of CMC, you can have at least 3 different approaches. So you can use stacked layers of fiber fabric, and that's 2-dimensional or 2D. You can take those stacked layers and you can needle them, and that is when you push literally a needle through the layers, and it picks up individual fibers and it pulls them from one layer to the next. So you end up with something in the Z direction. So the stacked 2D are all in the XY plane. The needles will have a small amount of fibers in the Z direction. And then you've got the truly woven 3D fiber preforms. The stacked 2G are the cheapest. The needled are a little bit more expensive, and the woven 3D are a lot more expensive. And then you can also look at how you make these materials. You can infiltrate them with slurries, you can infiltrate them with a molten metal, you can sinter them, you can pyrolyze them, or you can use chemical vapor infiltration. And the logos you can see on there relate to a previous Horizon 2020 program, which was known as CHARM. It finished in October 2020, and some of the partners were ISTEC in Italy, they were the leaders, the University of Birmingham, Airbus in Germany, and DLR in Germany. And we each took different routes, as you can see there. So ISTEC infiltrated with slurries and then sintered, Airbus infiltrated with slurries and then pyrolyzed, DLR infiltrated with melt, and Birmingham we infiltrated with slurries and then used CVI. And this was all to make ultra high temperature ceramic matrix composites. But the same concepts and exactly the same processing techniques can also be used to make Sig composites. So we've got the 3 different types, the 2D, the 2.5D, the woven D. Then if you want to impregnate with a slurry, we developed at Birmingham a process known as injection vacuum impregnation. I will describe that process to you a bit later on in this talk. And then you use your chemical vapor infiltration, and I will explain that process to you a little later in the talk. In fact, here it is. Chemical vapor infiltration. It's a process in which a solid matrix is deposited in a porous preform by the thermal decomposition of a reactive gas mixture. So you pass a gas at high temperature through a fiber preform, the gas breaks down and deposits a solid. And you can see three different chemical reactions there. Methane breaks down to give you carbon. A rather nasty gas called methyl trichlorosilane breaks down to give you silicon carbide. And zirconium chloride breaks down to give you, together with boron chloride, breaks down to give you zirconium diborides. And you've got many, many, many other chemical reactions that will also work. The process is a variant of chemical vapor deposition, which more people have heard about. In CVD, you get a coating, but in CVI, you get a solid body from a porous preform. And CVI is a commercial process. It is how carbon-carbon brakes are made for commercial aircraft. This is the process by which aircraft brakes are made. And also aerospace components are made out of CMCs composites using the same basic process. The advantage is a near net shape process. There's a wide range of compositions. The best one is that the processing temperature is typically less than 1,000 degrees centigrade, and that means you don't risk damaging the fibers. The matrix is pure and fine grained, and in situ, in the process itself, you can put different gases through. So you can start by depositing an interfacial layer, and then you can change the gas and deposit a different matrix. So these are all very good advantages. There are some disadvantages. The conventional process, isothermal, i.e. same temperature, isobaric, i.e. same pressure, is very slow. What do we mean by very slow? We mean that making each component can take about 1,000 hours. And that's about 3 months of processing time. That is slow. Now, you don't make your components one at a time. You have a very big chamber, and you there can make a large number of components at the same time. But it is still slow. Why is it slow? Well, if you look at the little diagram, hopefully you can see that the center, that the sample is the thing that's red, and the temperature, the color of the red is deeper in the middle. In other words, it is hottest at the surface and it is coolest in the middle. So when you pass your gases through, the gases tend to break down and deposit on the surface. And this blocks off the channels, the pores that lead the gases to the center of the body. So after a number of hours of processing, you stop the process, you take the part out, all the parts out, you machine the surface, then you put the parts back in, then you reheat the whole thing. Heating has to be very slow because we want to minimize temperature gradients, and then you go through the whole process again. And you might have to do the machining stage 2 or 3 times. And so the whole process can easily take 1,000 hours or about 3 months. Many people have done research trying to speed up the process using pressure and concentration gradients, temperature gradients, force flow, pulse flow. None of these, as far as I am aware, have ever been commercialized. What we are working on at the University of Birmingham is using microwave heating for the CMC composites and radio frequency heating for the carbon fiber-based composites. What that does is it means that the microwaves heat the silicon carbide fibers, or the radio frequency, the RF, heats the carbon fibers. And what you get is represented in that diagram now, where hopefully you can see that the center of the material, the red is brightest in the middle and darker at the surface. In other words, the center of the body is hotter than the surface. So microwaves heat from the inside out, and so does RF. And that means we now get our deposition in the middle of the body, and therefore we don't get this crust forming at the surface, and therefore we don't have to stop and machine. we can now do it all in one go. So we get much shorter processing times. And we can see this here. So this is actually for a SiC composite. So it's a silicon carbide composite. And what we've done, you can see the conditions there. It's 20 discs of fabric stacked and stitched together. And you can see the temperature is 900 and the pressure is 200 millibars and so forth. The time is just 4 hours. And if we then have a look at the surface of the composite, we have no deposit. That matrix you can see there isn't a matrix. In fact, it's just resin holding the fibers together while we polish the surface. But at the center, we've now got more or less complete deposition. So now you can see the circular fibers, and then all around them is silicon carbide. So at the center, after just 4 hours, the sample is fully cooked. And at an intermediate difference between the surface and the center, you've got a deposition of about a micron or 2 microns. So you can see that this is clear evidence that the inverse temperature profile really exists, and you get exactly the same results with RF CVI with carbon fiber-based composites. So this enables us to cook from the inside out. We can avoid all those machining stages, and we get much faster processing. And we can see the deposition profile here. So this is silicon carbide fibers with silicon carbide powder and a silicon carbide matrix. And what we are doing is we're taking the fiber preforms, we've infiltrated them with powder. Now we're depositing the matrix. And you can see when we heat it at 900 degrees centigrade, we get a nice inverse temperature profile in the middle. That's the area circled in red. At 950, that profile is larger, and by 1000, we've completely cooked the entire sample. Ignore the ends with the green circles. This is because we painted the ends of the samples with a silicon carbide slurry, and that was because we were getting electrical discharges where an individual silicon carbide fiber poked out of the edge of the sample. We built up the electric field in the microwave, and then just like lightning strikes, we got discharges. And we found by painting the ends of the sample, we could avoid that. So ignore the bits in green, it's the bits in red. And again, what you can see here is that you do indeed develop the inverse temperature profile. So it's nice to see that the theory actually is matched by experimental practice. And you can see here, these are the samples at 1000 degrees centigrade. The time is 8 hours. And you've got there, the center line is at 0 millimeters, and there's very little deposition. But as you move towards the surface, you get more and more deposition. So again, we're able to see from our samples that this whole inverse temperature profile works very, very nicely. And then we can check the rates. So on this plot, on the left-hand axis, you have got the mass gain rate, and the bottom axis is the pressure of the system. You can't operate at very, very low pressures because you get plasma discharge. If you operate at slightly higher pressures, you encourage arcing, but anything above about 150 millibars, we can operate successfully. And then you've got the plots at 900, which is roughly equivalent in deposition rate to conventional CVI. If you move to 950, you get faster deposition. And if you move to 1000, you get faster still. Note that data point that is circled, that's only had 5 hours rather than 8 hours. So after 8 hours of processing, we would expect it to be a little higher up that axis. That's an experiment we still need to do. So microwave heated CVI takes about 100 hours to make components. And that compares very favorably with the approximately 1,000 hours using conventional CVI. So we've speeded the process up by a factor of about 10. Most recently, we started a new program on using microwave CVI to produce hollow silicon carbide tubes. And this is for nuclear fuel cladding. So we wind our own tubes, as you can see in that top image. And then our partner is the National Nuclear Lab. We've got funding from the UK's Department for Business, Energy and Industrial Strategy, which is known as BEIS. It's part of a bigger programme involving other universities, as you can see from that bullet point, but what the bottom bullet point. But what we're working on is saying, well, so far we've only made discs or plates of material. Can you actually make a hollow tube? And the answer is yes, you can. We haven't finished the work yet. It is still ongoing. But you can see how with deposition time, after just 20 hours, the density is going up very nicely. And you can see there the estimated time to different densities, depending whether we're getting 0.1 grams per hour or 0.05 grams per hour. And it's suggesting, because we know we can get the 0.1, we're going to be 40 or 50 hours to make these samples. It's a long time, is 40 or 50 hours, but it's a lot better than 1,000 hours. Okay, so that concludes what I wanted to say about CMC composites. We're roughly halfway through the talk, so I wanted to spend the rest of the time talking about the ultra-high temperature materials. Now, these are materials that are needed to withstand really very high heat fluxes over very small areas. So you're going to get very high temperatures, oxidation and erosion, very, very high temperature gradients. Now, you've got some data on the right-hand side there. This all came from the US Air Force Research Laboratory, with whom I work quite closely. They did say to me, please don't show any numbers, so I've taken all the numbers off this, for which I apologize. In that top right image, what you have got is two sets of data. The blue represents something like the shuttle orbiter, so that curve you've got represents the front leading edge of the space shuttle. The red one is for a hypersonic vehicle, hypervelocity vehicle. So it's a much sharper leading edge. And you can see the consequences in terms of the heat flux. You have a much higher heat flux with the hypersonic vehicle, but you've also got a much, much narrower heat flux in terms of the position on the chord where the material actually sees the full temperature. And that then translates into the lower diagrams, which is the sharp leading edge. And you can see how it's really only the very, very front edge which gets hot. And then the blow up of that shows that even within that narrow band, it's really right at the tip that you get the extremely high temperatures. So we've got extremely high temperature gradients and very high temperatures. So the materials that we're looking at are ultra high temperature ceramics. They have the ultra high temperature capability. They have a high thermal conductivity, which is very good because it helps to dissipate the heat. And they have adequate, sufficient oxidation resistance. It would be better if that was better, but it's okay. The big disadvantage of these materials is they have a very low fracture toughness, 3 or 4 megapascal meters to the half. That's about the same as alumina, and that's just not good enough. And this is some work that was done in Italy. It's a few years ago now. This is 10 or 15 years old, but they made a nose cone for a rocket at the tip, just that, in that top image, just that little silvery bit right at the tip. That is made of zirconium diboride containing silicon carbide. And then it was tested. And if you look closely at the time, 15, 12, and 57 seconds. And within a second, that whole nose had completely failed. So it didn't survive 1 single second. So that tells us that these monolithic ceramics, not the composites, but the straight ceramic material, simply cannot cope with the temperature gradients that are generated. So the solution is to use composites. We can't use oxide fibers. They won't survive more than about 1,000 or 1,200. We can't really use silicon carbide fibers. They won't withstand more than 1,400 or 1,500. We can use carbon fibers, but they oxidize readily, so we've got to protect them from oxidation. So the carbon-carbon composite has excellent high temperature strength. It is very lightweight. It has a lovely low coefficient of thermal expansion. It has excellent ablation resistance, but It has extremely poor oxidation resistance above 500, and we want to heat these materials to 2,500 or 3,000 in air. So we need to find a way to improve the oxidation resistance. Okay, it's CVI processing again. You've already seen this. And so we're going to infiltrate the matrix using chemical vapor infiltration. So we start off with a powder, ultra high temperature ceramic powder, and it's actually in a slurry made of phenolic resin. We have a 2.5D or a 3D preform. We impregnate the slurry, we dry, we cure, we pyrolyze, and then we deposit carbon with CVI. So our matrix will actually be carbon. But let's just have a little look at the slurry impregnation stage. This is something that we developed at the University of Birmingham. Originally in the laboratory, we used vacuum impregnation, and it worked extremely well for small samples. But as soon as we started to make our samples bigger, we found that vacuum impregnation didn't work. You got that very shallow depth of penetration. These are micro CT, X-ray micro CT, microcomputer tomography images, and you can see how only the surface layers have got the material deposited. So we needed to find a new approach. We developed the injection vacuum impregnation, which we know as IVI. So you take a syringe full of your slurry, you plunge the syringe into your preform, and then as you withdraw the syringe, you squeeze the slurry into your preform. So now you're able to fill the preform from the inside with your slurry. And it works beautifully. It works absolutely beautifully. And you can get very, very homogeneously impregnated preforms, and it doesn't matter what the size is. So you can have a look at these things, and we shall see shortly, and you can make really large plates. The other big advantage is you use less processing steps. So with the old vacuum impregnation, you needed 8 different processing steps. And you can see the mass change there with each processing step. First PYR is first pyrolysis, and then second pyrolysis. The red shows the IVI approach. It takes just 3 processing steps: injection, impregnation, pyrolysis, and you've finished. You end up with something which is much denser. It's taken many less processing steps. So it's a much better route. We did a lot of work. On working out. So these are taking the preforms, injecting them with 1 injection, 3 injections, 9 injections, and more, and then working out using micro CT to work out how much the slurry spread. Since we did this work, we've had an entire PhD work on this to really understand the process and the science behind the process. We can use an automated system. So the injection was initially done by the student or the researcher injecting, and they ended up with a thumb that was really quite tired by the time they'd finished injecting a large plate. So we moved the whole thing onto an automated system. So we've got there an XY plotter. It moves the needle about and the syringe about, and then you apply the pressure with a peristaltic pump, and you squeeze down and you deposit an exact amount of slurry exactly where you want to put it in the preform. And so we learned that you apply an approach like this, where you start at the middle, you deposit at the middle, and then you work your way towards the outside. And there you can see the injection pattern for one sample. And then here you've got some samples. You can see the dimensions. Hopefully, you can see that the black is not absolutely uniform. So in the smaller sample, the black is pretty uniform. In the larger sample, hopefully you can see in the top right-hand corner and in the bottom right-hand corner, it's a slightly different shade of black. It's a bit lighter gray. That's where it hadn't completely impregnated it. But nevertheless, that is part of the learning curve, and we can now produce samples that are almost any size, any thickness, any size, and we can get a very, very, very homogeneous powder dispersion within them with this technique. And of course, this whole concept of injection-based processing is applicable to far more than just making ceramic matrix composites. Okay, so we've seen this slide before. We've done the slurry impregnation. We dry everything out. We cure the resin that's in there. We pyrolyze the resin, and that gives us some carbon. And then we use the CVI system to deposit the rest of the carbon matrix. We use RF processing now, not microwave, because we are using carbon fibers, and carbon fibers absorb RF. Silicon carbide fibers absorb microwaves. So the different frequency, different wavelength applies to different materials. And again, you can see here the inside out infiltration. So you've got the center one there, and you've got about 4 microns of deposition. This is after just 2 hours of depositing. 12 millimeters from the center in either direction, and you've deposited about 1.2 microns of deposit. So again, nice clear evidence that we are getting our inverse temperature profile. Okay, so then we make the composites. This is a 2.5D preform. So this, remember, is stacked layers of fabric, and then you needle them going through, and the needle goes down, gets hold of some fibers from the layer below and pulls them back to the layer above. And so we've got something in the Z direction. We found we can get very uniform RF heating, which is excellent. And we found that after just 21 hours of infiltration, we can get 10 volume percent porosity. So it's 90% dense. With conventional CVI, to get 10 or 11% porosity, 89–90% dense, as we have said, you're looking at about 1,000 hours. So in this case, it's now roughly 40 times faster. With 3D preforms, it's a little different. 3D is slower. After 16 hours of infiltration, we still have 30% porosity. It's only 70% dense. And the reason for that is that the gas permeability for the 3D preforms is much lower than for the 2.5D preforms. And if we can't get the gas to flow through the sample, then we're not going to be able to deposit the matrix. So it's much, much slower because the preforms have much less gas permeability. The advantage they potentially offer is improved mechanical performance. So most of our work has been done on the 2.5D Panox. You can see the structure of the 2.5D. So 23% fiber, 77% porosity when we start. The bulk densities about 0.36 grams per centimeter cubed. And what you do is they're stacked in a 90-0 layer, and then you get this random orientation which arises from the needling process as you pull the fibers from one layer into the one above. The 3D samples, they're made of pan fiber. They're actually made by a process. It's a fairly new process. It's not weaving, it's called nubing. It was developed in Sweden. The company is Parejo, and we bought 2 fabric layers to begin with. They are not cheap. They are not cheap fabrics. 40 volume percent and 65 volume percent was what we got originally. And you can see the different weaves that, and you can choose anything that you want to do in terms of the weave. You can have as much or as little fiber in the X, the Y, and the Z direction. So it's a fantastic process. It just isn't cheap. And the 65 volume percent was an absolute disaster. It just didn't allow the gas to flow anything like the required rate. So then we bought some 23 volume percent, and you can understand why 23, because our 2.5D was 23. And so now we're able to compare a 2D and a 2.5D and a 3D, both at 23 volume percent. We've also focused on scaling up. A lot of our work was done at the beginning on quite small samples, 50 millimeters, but we did a lot of work including modeling of the whole RF process. So we could go from 50 to 100, and then we want to get to 200, and then we want to get to 280 millimeters. All of this work should have been finished a year or more ago, but the pandemic, of course, closed our labs for several months. Now we're operating again. We have been since about September, but with reduced numbers of students in each laboratory. So each researcher is typically getting about 2 or 3 days a week in the lab, because we're only allowed 2 people in a lab at a given time. And so it has delayed our whole process by at least a year. So hopefully, the new system will be operational this summer. We've also done some work on depositing not just a carbon matrix, but actually a zirconium diboride matrix. So we flow a mixture of boron chloride and zirconium chloride in an argon carrier gas through the system. You can see the RF system there. It's a simple tube with a coil around it, heats the sample up, deposits the material. There on the top right, you have got the equation, and the question is, does it work? And the answer is, yes, it does. So here is just after the first hour or so of deposition. You've got the fibers, you can see the deposits starting to occur on the surface of the fibers. If we zoom in a bit, you can see the fibers are quite nicely coated in the deposit. And when we analyze that, we find, yes, it is zirconium diboride. And the idea here is that in use, if you have any cracks, the zirconium diboride will oxidize to zirconia, and hopefully that will seal the cracks. So the idea here is to see if we can achieve some crack sealing, and therefore get even better materials. So the RF CVI process, it has a number of advantages. It yields a good microstructure. It's a low temperature process. There's no damage to the fibers. It's possible to deposit fiber coatings or change the matrix by changing the process gas, but it has some disadvantages. At 24 hours, it's still a fairly slow process. Residual porosity does limit the strength. CVI, you won't get much more than 90% dense. Scaling up is only just started, and of course, costs are unknown. So very quickly, because I know I'm running out of a bit of time, looking at the silicon carbide composites, when we put the silicon carbide powder in there, what effectively we're doing is we're filling up the voids. So that top left figure, you've got quite large voids. This is a micro CT, up to 700 microns in size. And that's quite a big void. We can fill them with the powder, so that helps nicely. In the carbon fiber ultra high temperature ceramic system, it's quite different. Here is a material being tested. I'll explain more about the testing shortly. This is an oxyacetylene torch. But there's the location of the flame tip. You can see, I hope, some solidified material that used to be molten hafnia. And if we look at the structure of the material, you can see this is the fiber, preformed carbon fibers coated in what is now hafnia, what was hafnium diboride. So we're looking to the right of the hot point. And if we zoom in, we can see that the hafnia, which is formed as the hafnium diboride oxidizes, it's sintered. And then if we look down the hole itself, you can see here some regions, gray regions. They are actually formerly molten hafnia. So we know we're above the melting point of hafnia. And if we zoom in, you can actually see we have a non-wetting situation. So our what was molten hafnia has formed droplets, and they are not wetting the carbon fibers. So we've got partial wetting. We think we can improve the performance if we achieve better wetting of the carbon fibers. And if we zoom in even more, we can see we've got crystalline hafnia. So initially, the powder adjacent to the maximum temperature sinters and protects the fibers. However, the question was, how does the molten hafnia formed at the maximum temperature protect the fibers? And to answer that, we felt we needed to measure the viscosity of molten hafnia at 3000 degrees centigrade. And we managed to find a chap, Dr. Louis Hennet. He is based at CNRS in Orléans in France, and this is exactly what he does. This is his research areas. He measures the viscosity of molten materials. So this is his figure, not mine. And right in the center of it, you can see the black droplet, the spherical black droplet. That is the molten material, and it is supported on a gas flow. So it's kept levitated, it's kept supported by the gas flow. And then he has a wide range of systems around it, which includes some speakers. Actually, he told me these are this is a speaker he took from his daughter's hi-fi system at home. He said she wasn't too impressed, and he hasn't returned it to her yet. And what he does is he blasts some sound at the droplet, causing the droplet, which is levitated, to vibrate. And this is the vibrating droplet. There is a droplet of molten hafnia at 3000 degrees centigrade, and then it vibrates, and then the vibration stops. If we just see that again, you can see the droplet vibrates, and then the damping in the system causes it to stop. And by monitoring that damping, he can get the values that he needs. So on the left-hand side, you have got viscosity versus temperature. And on the right-hand side, you've got surface tension versus temperature. And you can see hafnia is more viscous than zirconia, and zirconia has a higher surface tension than hafnia. And you can see also that the viscosity decreases with temperature, which is exactly what you would expect. So we've now got values for surface tension and viscosity. And if you look at those values, you realize that the viscosity is really low. So we are not getting protection at all from our molten oxide. These are fragile liquids. This material is not going to survive an oxyacetylene torch's gas blast at very short range. So we need to find another explanation. So let's have a quick look at our thermoablative testing. We've tested them two ways: the oxyacetylene torch. We also have an oxypropane torch and an arc jet tester. The oxyacetylene and oxypropane torch, this is at the University of Birmingham. We built it ourselves. So we have all the system which is set there. The sample is on the left-hand side of that figure. It's 0.4. Then you've got the torch itself, and we can measure the temperature using both a thermal imaging camera and a two-color pyrometer. And at the bottom there, you can see some of the conditions. The oxyacetylene, 2,950 is the highest temperature we've measured. With the oxypropane, about 2,500. The heat fluxes, the heating rates, about 1,000 degrees centigrade per second. And we've measured the gas velocity, and it's about Mach 0.6 in both cases. And there you can see the oxyacetylene torch on the left and the oxypropane torch on the right. The oxyacetylene torch, the OAT as we call it, is a single point source of energy. The oxypropane torch is multiple flames. And this is the oxyacetylene torch test. It's been edited. It was a 5-minute test. We've edited it down to a few seconds. There is the sample coming in. You can see the heating rate. We can then put a filter in, and we can actually watch what is happening to the surface of the sample during the test. Then we allow it to cool. This is the slowest part of the test. So we typically test materials for about 5 minutes. We'll just watch that again. There it is. There's the sample coming in. You can see the extreme heat rate. You can see how close the flame is to the sample. And then we've edited this down. And the sample at the end of the day has 0 erosion. This was one of our materials we developed later in the program. And there you can see a whole series of heating rates and different materials will have different heating rates because of their different thermal conductivity. We've also developed the process where we can now do it at 90 degrees, which is where we started, but also, as you can see, we can move the torch around. So now we can have angles varying from almost 0, about 5 degrees, right through to 90 degrees. So we can investigate the effects of a glancing flame on the surface. These are some of the results. These are 2,950 for 300 seconds. This was comparing the old VI against IVI process, and you can see the IVI samples were much better. The depth of the ablation hole was smaller and the erosion was significantly less. A much better test and a much more expensive test is the ArcJet. So we developed our systems for rapid screening. Is material A better or worse than material B? When you really want the testing done and you want to get results for publishing, you really need ArcJet testing. But these tests will cost something like 25,000 euros per sample. So this is not a cheap test, but it actually uses much larger heat fluxes. The temperatures are much the same, but the gas speed is now truly supersonic or hypersonic. So it's a most realistic test you can do. There's only a small number of systems in the world, NASA, AFRL and DLR. Our materials have been tested at AFRL in the United States and DLR in Germany. So here's our samples at the beginning, and there is an image of the sample being tested, and here are the images of the sample after the test. Very short times, 20 seconds, 10 seconds, but in that bottom one at 10 megawatts per meter squared, you can see splashes of what was molten hafnium after the test. We've had a lot of tests done in the charm process. This is the DLR system that tested it. You can see the conditions that we use for testing. Here is the sample all lined up. The bottom left-hand image there is of one of our samples actually being tested. And this is what comes out at the end. And we had one sample, we tested it 4 separate times, up to the first, the second, the third, and the 4th cycle. And you can see this sample is doing fine. It's surviving 4 separate cycles here. And then each time the thickness was measured, the mass was measured. And what you've got there is how the temperature, that plot in the bottom right-hand corner, is how the temperature changes as a result of time. And you can see it really, really uniform. There's a bit of variation in the first 20 seconds, but then after the second cycle, the material settles down and it just performs beautifully. So what do we know? We know that carbon fiber, hafnium diboride and hafnium carbide generally outperform other systems. There are more systems you can look at. We know the hafnium carbide isn't great. It results in the front face falling off, whereas the hafnium diboride is much better. We know the hafnium diboride based composites can withstand 3000 degrees centigrade for quite a few minutes. Zirconium diboride will go to about 2,500 degrees centigrade for many minutes. It is a lower temperature material, but it's half the mass and is a whole order of magnitude cheaper. So if you don't need the 3,000, if 2,500 will do, then you want to use zirconium diboride. Silicon carbide additions can improve the oxidation, but only up to relatively modest temperatures. And then the final thing is just to show you that this was an amazing discovery we made a couple of years ago. And this is the amount of hafnium diboride. So this is mixes of hafnium diboride and zirconium diboride. And you can see these are the mass ablation rate and the linear ablation rate. So lower is better and the ablation area smaller is better. And you can see that if you have 100% zirconium diboride, you get something, you can see that you get quite a bit of damage. 100% hafnium diboride, you get less damage. But actually, 75% hafnium diboride, 25% zirconium diboride gives you the least damage of all. And we are still working to understand why this is. We know from images that you get a different attack pattern. And this is something we really need to understand. I was supposed to have a PhD student start in October last year. The student hasn't been particularly well and so is joining us in October this year, I hope. And then that PhD student will try and investigate what is happening here and try and come up with an explanation for why the 75% hafnium diboride composition is by far the best. And you can see that's what the sample looks like. You can see those splashes of molten zirconia. With hafnium diboride, it's broadly similar, but with that mixture, you get a different pattern, and we need to understand that pattern. Okay, so performance, we can achieve quite a bit. Properties, the question is, can we make components? The answer is yes, we can. Here is a jet vane that we made. It was successfully tested at 2,550, 6 megawatts per meter squared, Mach 0.6, and that survived very, very happily. So it was designed by MBDA engineers working with us. It was made by us, and at the very first attempt, it passed and was successful. And what we did was we designed the micro and the macro structure to yield the design properties. And in just a few months, we had made a component that was very successful. In the CHARM project, we've made very large samples, and we've also made rocket nozzles, as you can see there. And fabrication, can parts be made at reasonable cost? Well, we did a very crude manufacturing cost analysis, and all I can say is the company didn't run away but gave us more money. So I assume that the costs they consider to be reasonable. Okay, that's it. Thank you very much. It is now becoming possible to design and manufacture materials that can withstand a range of demanding environments, 1,000 up to 3,000. Heat fluxes up to tens of megawatts and gas flows up to hypersonic. For me, the key to success is utilizing our knowledge of the processing microstructure properties relationships. By doing so, we can actually design materials, make them, test them, and we are finding they are being successful. We are scaling up all of our different programs, and we hope that the future work will begin to examine the potential for even more compositional variation and control. Thank you very much for your attention. That concludes this presentation.
Well, thank you so much. We have some. We have some questions. You can see them in our chat.
Questions? Okay. Can we call ceramic matrix composites eco-friendly and sustainable? That is a really good question. Not particularly at the moment. I don't think we honestly can, but just earlier this week, I was involved, on Monday this week, I was involved in a major conversation with a number of other UK partners where we were discussing exactly this point. So I think the focus up to now has been on, can we make materials that will do what we want them to do? And the answer pretty much is coming back yes. The work isn't finished, but it's coming back yes. Now the next question that we're asking is exactly your question. Can we do them in an eco-friendly and sustainable way? I think we can. I think our process, although we didn't intend this as the primary goal, I'll be absolutely honest, is a lot more eco-friendly and sustainable. A process that lasts 20 hours is clearly a lot more eco-friendly than a process that lasts 1,000 hours. That is almost accidental. It's delightful, it's great, but I won't pretend that was our target. But I think where the eco-friendliness and sustainability will come in is also in how are these materials used, and what part of our discussion on Monday focused on, which is not really been looked at for any ceramic before now, except with a very small number of exceptions, is what can you do with the ceramic after the end of its life? There are a very small number of examples. For example, in the refractories industry, some refractories then get used in making road surfaces, certainly in the UK. I can't speak for other countries. But the number of examples where that happens is very small. And one of the things we were discussing on Monday, not just for these materials, but for ceramics in general, is how can we achieve that more? How can we find a new use for the material after the end of its life? So this is very much something that is being discussed at the moment. What is the future of ceramic matrix composites? What traditional and composite materials can they substitute on a broader scale in the future? The future for ceramic matrix composites generally, I think, is really very positive. One of the things they do, for example, silicon carbide composites, they can survive much higher temperatures than aerospace alloys. So they allow things like the jet engine, civilian jet engine, to operate at a higher temperature. The higher the temperature, within limits, the higher the temperature, the more fuel efficient it is. So you can imagine a jet plane taking off from Moscow and flying to New York will use less fuel for the journey if it's got silicon carbide parts rather than pneumonic alloy or whatever parts. Or alternatively, it could be a bigger plane and carry more people. It will be more fuel efficient. That's good, clearly. It's not as good as nobody flying at all, but it's if we take the line, we want people to be able to fly around the planet, then the more fuel efficient the engine, the better that has to be. So I think you will see that future jet engines will incorporate a lot more ceramic matrix composites, and they will be a lot more fuel efficient. And you can apply similar logic elsewhere. It's less applicable in cars, but there are certain advantages, again, you can find with cars by taking mass out. But things like the jet engine is a major advantage. And there are many other applications in aerospace especially where this can be true. Blasting satellites off into space, for example, you may be able to achieve a lot more advantages there by having more reusable systems. So in rockets, the rocket nozzle usually gets used once, and that's the end of the day. It's a carbon-carbon composite. Well, if you adopt some of these materials, you can imagine the rocket nozzle being used 5 times, 10 times, 20 times. I don't know how many. We haven't done those experiments yet, but many more times. And again, that is getting more eco-friendly. What is the most effective way to reduce the cost of ceramic matrix composites, in your opinion? I'm going to give you an indirect answer to that, if I may. I think the most effective way is to stop and think, what do we really want here? That's how we made our carbon fiber ultra high temperature ceramic composites. It's very easy to go into the lab and just do lots and lots and lots of experiments and be very busy and not really think deeply about what you're doing. What we did was we worked backwards. What properties do we want to achieve? How are we then going to achieve those properties? What chemistry, what composition do we want it to be? And what microstructure do we want to achieve? And then how do we achieve that combination of composition and microstructure? And so the work actually was done in a matter of weeks and months to, as in far less than a year, to actually come up with that working jet vane. And I think that's one of the routes forward. At the moment, I think, and I'm criticizing my own team and myself as much as anybody else, but I think we tend not to have deep enough thinks about what do I really want and how can I achieve it in the shortest possible time, whilst making sure we do achieve it. And I think rather than, and also the other big thing that I would say is that there are too many people, too many researchers, too many scientists who attach themselves to one idea. They've been doing it for the last 5 or 10 years and they are determined to make it a success. And they will ignore results that show that their route is not the best route. And one classic example of this, in the ultra high temperature ceramic composites area, people want to put silicon carbide in. And that's fine, that is fine. But And they will tell you that by addition of silicon carbide, you will increase the oxidation resistance. And that is a true statement, provided the temperature of application is 1700, 1800, and certainly no more. And if you're operating at those temperatures, actually, are these the best materials? Maybe there are other better materials to operate. But they have been working on this for 5 or 10 years in some cases, and they just don't want to say, actually, yeah, I think you're right, let's do it a different way. And I think we can all be guilty of that, me as well as anybody else. You get an idea, you focus on the idea, you convince yourself it's right, and then you actually close your mind to the fact that this may not be the best way. So I think it may not be the answer you were expecting, but what is the most effective way to reduce the cost of these materials? I would argue it's to keep an open mind. Costs will come down as we use more of them. The fibers at the moment are really expensive. But that was true of ceramics in the 1970s. They were really expensive. As we use more and more of them, the costs come down. So that is good. But rather than just wait for that situation to happen, I think having a really good think about what you really want to achieve and bringing in our first question, how can we make all these things more eco-friendly, and doing that right at the beginning. So my team has always considered eventual costs throughout the research. And there may be some directions we simply don't pursue with any rigor because we know the answer will be, it's going to be too expensive to use. We might do a few experiments just to sort of, okay, but what would the answer be? But we won't pursue it seriously. We will consider costs. And I think increasingly, especially the generations to come after me, really need to have that eco-friendly, sustainable approach in their research, like costs, right from the outset. So that's, I think, the answer to that question. Which countries are going to become leaders? That's an extremely difficult one to answer. I hope, in a way, the answer is none. And I don't mean that in a strange way. I hope, my dream, for what it's worth, is that actually competition is good provided it's controlled. Competition can be a really good thing. It can spur you on. I want my team to be better than that team in France, or I want my team to be better than that team in America or China. That can be good. It makes us all work harder. But competition can also be destructive. And what I would like to see is a lot, and I mean a lot, more international cooperation. One of the arguments I've been using, it hasn't been the most successful thing I've ever done, but one of the arguments I've been using is actually on the basic science, we can all collaborate. And then what we do is we take the science we've developed and we turn it into engineering, and in the engineering stage, we compete. But we collaborate to compete. Ultimately, we will compete on the engineering, but we collaborate on the science. And it would be lovely to see a Russian team and a Chinese team and an American team and a European team really working well together on the basic science. And then we take our results and the Americans do what they want to do with it, and the Russians do, and the Chinese do, and the Europeans do. And what we then do is we compete with each other, but at the engineering stage, but we've worked together on the science. So I would hope the answer to your question is let's collaborate a bit more, especially in the early stages on the basic science. Which part of the processing of CSCs is making their production the most expensive? To be honest, the answer to that is not the processing, it's the fibers themselves. Ceramic fibers are really not cheap. Part of that is the fact that they are just expensive to make. Part of that is the fact that we're really not using them in huge quantities. So silicon carbide fibers tend to be made mainly by the Japanese. They're very good fibers. But you get stories, I don't know if these stories are true or not, but you get stories like, you know, they've already sold all of their 2021 production, and this was back in 2020. So in other words, everything they ever make is already sold. Now, how does that help keep prices down? You know, supply and demand, and if the demand greatly outstrips the supply, prices go up. And so one of the things we do need to do is to be able to keep these prices down. Part of it is just using more, then you get economies of scale, but part of it is also having a desire to actively want to reduce the prices. And at the moment, if you are a company and everything you can ever make, you know you can sell with no effort really on your part, where's the incentive to bring the cost down? And again, I think part of this could be greater collaboration at the science level and then leave the competition to the engineering level.